Here we're going to take a look at continuous functions. Now the goal of this section is to precisely define what is meant by continuity of a function. And continuous functions are important since many of our theorems in calculus require the use of continuous functions. So you may see a theorem stated like, let f of x be a continuous function, then whatever. Now in a previous math course, you may have been told that a function is continuous if you can draw a graph without picking up your pencil. Now that's perfectly true, and that's a starting point for defining what continuity means, but it's not really a definition that we can work with to precisely prove or disprove that a function is continuous or not, nor can we use it in the proof of other theorems. So we need to come up with a very precise definition. So to begin, we're going to consider a set of graphs, and we're going to look at these graphs and determine which ones we think should be continuous and which ones are not continuous, and then from there we're going to build a precise definition. So down here we have the graph of 5 different functions, and we want to ask ourselves which ones appear to be continuous when x is equal to c. Now we're going to start with that basic definition that the function will be continuous at c if we can draw the graph through x equaling c without picking up our pencil. So for number 1 here, notice if I try to draw the graph, I actually have to pick up the pencil and then move up to the black dot here and continue on. So this one does not look like it should be continuous at x equaling c. Number 2, same thing, I draw the graph here, and then I have to pick up my pencil, put that little black dot there. That's actually f of c right there on the y-axis if you move over. Then come back down and continue. So no, that one doesn't look like it should be continuous. Number 3, draw the graph with my pencil, then I actually have to hop over that little opening and continue. So no, this graph doesn't look like it should be continuous either. In this graph right here, f of c is actually undefined. If you draw a vertical line, you actually never hit the graph, so f of c is undefined. This one over here definitely doesn't look like it should be continuous. This graph actually goes all the way up to positive infinity, and you have to sort of hop over and continue on the other side with your pencil, come all the way down like this, so no, that one shouldn't be continuous either. And then number 5 here, well, that one, actually, if we draw the graph here, I can continue right through that point right there is c, f of c, and then I just continue, and I did not have to pick up my pencil. So yes, this one does look like it should be continuous. Now let's take a look at a definition and see that this definition is satisfied by graph number 5, but not by the other 4 graphs. And that'll be our working definition for a continuous function. So here is our definition. So we say that a function f of x is said to be continuous at x equaling c if the following conditions hold. First of all, f of c must exist. Second, the limit as x approaches c of f of c has to equal some number L. It exists. The limit exists. And then finally, number 3, f of c actually equals L. Now let's take a look at these graphs up here and see that only graph number 5 satisfies all 3 of these conditions. So we'll just label those conditions like as 1, 2, and 3 and see which ones are being satisfied up here for each. Alright, so for the first graph here, it does look like f of c is satisfied. It exists. Number 1 is satisfied. F of c would be whatever that number right there is on the y-axis. So number 1 is satisfied. Number 2, the limit as x approaches c of f of x, that does not exist, right? because the right and left-hand limits would be different numbers. Okay? You see, as you approach c from the left, f of x is approaching that number on the y-axis, and as you approach c from the right, you're approaching this number on the y-axis. So f of x is not approaching a single number, so the limit does not exist. And if the limit doesn't exist, number 3 can't be satisfied either. All right. Number 2, f of c, yes, it does exist. It is whatever that number right there is. That is f of c right there on the y-axis if we move over. Number 2, the limit as x approaches c of f of x, well, as I approach c from the left and from the right, my function is getting closer to actually this number right here on the y-axis. That would be the L. You see that as I move this way, the y values are getting closer to that number from both directions. So 1 is satisfied, 2 is satisfied. However, as you can see, f of c doesn't equal L, so 3 is not satisfied. Number 3, well, f of c is not defined, right? If I draw a vertical line, I never hit the graph. So number 1 is not satisfied. Number 2 is satisfied. F of the limit would be that number right there on the y-axis. But number 3 can't be satisfied because f of c doesn't exist, so I can't say f of c equals L. Number 4 here, well, this is a pretty bad one. Number 1 is not satisfied. F of c is undefined. Number 2 is definitely not satisfied. This limit does not exist. The function is not approaching a single number. It is going up to infinity, but it's not approaching a single number that exists. And then number 3 can't be satisfied either. Okay. Now let's finally take a look at number 5. All right, first of all, f of c, it does exist. Right there it is on the y-axis. Okay, if I go over. So number 1 is satisfied. Number 2, the limit, well, yeah, the limit is the same number right there on the y-axis. So the limit exists. And then we see that f of c does equal L. So, you see, the reason we use this definition is because it works when we think it should work, and it doesn't work when we think it should not work. That's how mathematicians come up with definitions. They think about, they start out with a base definition, an intuitive definition, like I should be able to graph the function without picking up my pencil, and then they think of various cases where their definition should work and when it shouldn't work, and then they try to come up with a definition that works in certain cases and fails to work in other cases. That's how they come up. That's how we come up with definitions in mathematics. Okay, so this is our definition now. Let's take a look at some examples, how we work with it. Now, notice this one thing here. Sometimes you'll see conditions 1 through 3 combined into a single statement, where we say f of x is continuous at x equaling c, provided that the limit as x approaches c of f of x equals f of c exists. If this holds, that's really combining 1, 2, and 3 into one statement, because you see, you're saying f of c exists. At the same time, you're saying the limit as x approaches c of f of x equals that number, f of c, right? So the limit exists. And then, of course, f of c equals the limit. So this is really combining all 3 statements into one. But it's nice to split the definition up into 3 separate parts like this as we're working through the examples. You'll see that it's nice to do that. And also when we talk about removable discontinuities, it's easier to have the definition broken up into 3 parts like this. All right, so let's take a look at a few examples now. We've already done this example. looking at the 5 previous graphs and determining which conditions are satisfied and which fail. So let's take a look at this example now. So for this function, f of x equals 1 over x minus 1, we want to determine if it is continuous at x equaling 1. Alright, so we have to look at our 3 conditions. First of all, we need to see if f of 1 is defined. Well, obviously in this case right away we see f of 1 is 1 over 1 minus 1. Well, that's 1 over 0. That's undefined, right? Undefined. So f of 1 does not exist, so right away condition 1 fails, so we know this is not going to be a continuous function at x equaling 1. Now let's just check the other 2 conditions. Well, certainly the limit is not going to exist either. Limit as x approaches 1 of 1 over x minus 1. Well, that's going to DNE, right? Because the top is approaching 1 as x approaches 1. The bottom is approaching 0. Well, it depends either from the right or the left it's approaching 0, depending on which side x is approaching 1 from. And so this limit is going to DNE. So number 2 is not satisfied, and then number 3 can't be satisfied because f of 1 is undefined and the limit does not exist as well. So this function is definitely not continuous at x equaling 1. Here's what its graph looks like. Okay, obviously with this graph I cannot draw the graph without picking up my pencil like that. So obviously that fails the definition for continuity as well as the intuitive definition for continuity of being able to graph it without picking up your pencil. So it fails the precise definition and the intuitive definition as well, of course. Let's take a look at this example. So let's determine if f of x equals x squared plus 2x plus 3 is continuous at x equaling 1. Alright, so let's check out our 3 conditions. First of all, we have to look at f of 1. Well, is it defined? Well, can I put 1 in here for x? Well, of course I can. I can put 1 in there and we get back 6. So yes, condition 1 is satisfied. What about the limit? Well, from our limit results, we can just plug the number 1 in here for x, and let's see what we get back. Well, we're going to get, of course, 1 squared plus 2 times 1 plus 3, which is, of course, 6. Okay, so the limit exists. It is a finite number. And then we see that f of 1 does equal the limit, right? This 6 and that 6 right there, they are equal, of course. And so condition 3 is satisfied. Okay, so this function is definitely continuous at x equaling 1. And if we take a look at its graph, right here is the point. That is the point right there, 1, 6 on the graph. And of course I can graph that function nicely with my pencil without picking up my pencil and go right through that point. So yep, this function is continuous. Okay, let's take a look at this one. Now this is a piecewise defined function, and we want to see if it's continuous at x equaling 1. Alright, so we have to look at our conditions. Let's look at f of 1. Alright, so f of 1, well, when x equals 1, I'm supposed to say f of x equals 3. It's a piecewise defined function, and so this is 3. I just follow the definition. That is defined. It exists, so condition 1 is satisfied. Well, we need to take a look now at the limit. So what is the limit as x converges to 1 of f of x? Well, that's equal to the limit. I have to use this piece of the function, the x squared minus 1 over x minus 1. Now, to evaluate this limit here, Notice if I put 1 in for x, I get 0 over 0. That indicates the limit may exist, so, well, we'll try the cancellation technique. Notice we can factor the top as x minus 1. So this equals the limit. And that, of course, is 2. I can just plug the 1 in for the x now. Okay, so the limit does exist, so condition 2 is satisfied. However, we notice that the 3 does not equal the 2, right? And so condition 3 is not satisfied. So this function is not continuous at x equaling 1. It's almost continuous, but not quite. Let's take a look at its graph and see what's happening here. So here's what the graph of this function looks like. You notice if I try to graph it with my pencil, I do have to pick up my pencil, fill in that little dot, come back, and keep going. So we see that this is not continuous by our intuitive definition, and it's also not continuous by our precise definition. You notice that the limit, we showed the limit was 2, and that's what we see from the graph. The limit is 2 right there, and the function was defined at 1 to be 3, and so we see here 2 does not equal 3, so that's why our function is not continuous. Alright, now notice this one thing down here. Notice that we could make this function continuous. All I would have to do is to take that little point right there and move it down here and fill in that hole in the graph. So we see that f of x can be made continuous by just redefining f of 1 to be the number 2. Instead of defining f of 1 to be 3, as was defined in the function, if we had said f of 1 were equal to 2, then this function would have been continuous. That would have been like moving that dot right down there and filling in that hole. We're going to call that type of discontinuity a removable discontinuity, and we'll state that precisely down here. Alright, so here's our definition for a removable discontinuity. So we say f of x has a removable discontinuity at x equaling c if f of x is not continuous at c, but the limit does exist. Alright, so if our limit exists, but the function's not continuous, then we say it has removable discontinuity, and we note that f of x can be made continuous at x equaling c by redefining f of c to be L, which is what the limit is. Alright, so that's how f of x could be made continuous, and that's exactly what we saw up here. So let's take a look at these examples. For the following functions, both of these functions are not continuous at 3, because you see if I put 3 in for x, I get 0 in the denominator, so f of 3 is undefined. But let's see which ones have removable discontinuities. So let's take a look at the first one. Alright, so for the first one here, we need to look at the limit as x converges to 3 of, and we have to see if this exists. If it exists, this function might be, we might be able to redefine it at 3 to make it continuous, so the discontinuity would be removable. Well, let's see, as x approaches 3, what's the numerator doing? Well, the numerator, this is what? This is approaching 27 plus 18 plus 1, right? If I plug 3 in for the x here, and just add the 1 to it, we get this, which is what, 46, right? So the top is approaching the number 46. The bottom, however, is approaching 0. 46, of course, is non-zero. This limit has no hope of existing. So no, this function does not have a removable discontinuity at x equaling 3. The limit is not going to exist. So number 1 has a non-removable discontinuity. All right. Let's take a look at number 2. So for the second function, notice that this is definitely not continuous because f of 3 is undefined. If I put 3 in here for x, I get 0 in the denominator. But let's take a look at the limit. If we look at the limit of this function, well, let's see. If we put 3 for x into the numerator and into the denominator, you'll notice that we get back 27 plus 9 minus 36. That's 0. And in the denominator, we get 0 as well. This limit has a chance of existing. So let's see if we can do some cancellation here. So limit. Now the top will factor as, if I factor out an x, then I'm left with a quadratic, x squared plus x minus 12, and that factors as and then of course I can cancel these 3 x minus 3's and we get the limit. And then so this, now I can just plug the 3 in for the x's. I get 3 times 7 or 20. So this function has a removable discontinuity because the limit does exist. So this has a removable discontinuity at x equaling 3. In fact, all we would have to do is redefine this function to be Alright, we would just have to redefine it like this. This would be a continuous function because f of 3 would be 21. The limit of this function would be the limit of this term as x approaches 3. That is 21. They're equal. Alright, and so conditions 1, 2, and 3 are all satisfied for this. Notice actually that this function here is exactly the same then as just x times x plus 4 everywhere. That's really what this function is. By filling in that little gap, the hole where this function is undefined when x is 3, by filling in that hole, we're just doing this, and then this is just equal to x times x plus 4. Notice if I put 3 in here, I do get 21. And notice that if we come back to our original function here, if we were to do all the cancellation, factor the numerator denominator, cancel the x minus 3's, we get x times x plus 4. So that's all that we would be doing here. Okay, let's take a look at this one. So for this example, we have a rational function, x squared minus 5x plus 6 over x cubed minus 7x squared plus 10x, and we want to find where it has any discontinuities and determine if any are removable. So first of all, the discontinuities are going to occur wherever the denominator is equal to 0. So let's set that equal to 0 and see what we get. Now let's see, this factors as, and this term here further factors as, and this has solutions Alright, so this is where at these points 0, 5, and 2, those are the values where the function is not going to be continuous. Now let's determine if any of these are removable. Well, notice the top, we can actually factor that. So let's take a look at that as well. So if we look at, let's start with the function f of x. Notice the top will factor like this. The numerator factors as. And we've already denoted that noted that the denominator factors as. Now we see here that the x minus 2's cancel. That's going to indicate that the 2 is a removable discontinuity because they cancel. And more precisely, it also indicates that the limit as x approaches 2 of f of x exists. Because of this cancellation, that limit will exist. So you notice that the limit as x approaches 2 Now, as x approaches 2, it never actually touches 2, or it never equals 2. X is never equal to 2, so we're justified in canceling these, and we get and now you see we can plug 2 in for each of these x's, and we do get a value back. And this value exists. So therefore, since the limit as x approaches 2 exists, 2 is actually a removable discontinuity. So therefore your discontinuities are at, and the removable discontinuities are when x is 2. And so therefore this function up here is going to be continuous over these intervals. So these are the intervals over which the function f is continuous. Notice we basically took the real numbers here and we took away 0, 2, and 5 from it. So it's basically the real numbers minus the set of numbers 0, 2, and 5. So this is your interval of continuity for this particular function, with 2 actually being a removable discontinuity, as we indicated over here. And here's what the graph of this function looks like. You notice that the function is undefined when x is 0. We have a vertical asymptote when x is equal to 0, so the function is undefined there. We have another discontinuity at x equaling 5. Another vertical asymptote occurs there. And also notice that at 2 we have this little open circle right here. That indicates that technically the function is undefined at 2, but if I wanted to, I could fill in that little circle right there and make the function continuous. Notice the function is undefined at 2 because if we plug 2 in here for x, we get that f of 2 is equal to 0 over 0, which is an undefined number. So the function technically has a discontinuity at 2, although it is removable. We could cancel those x minus 2 terms and end up with a function that actually is continuous at 2 if we were to only look at x minus 3 over x times x minus 5. See, by canceling, then we've removed the discontinuity. But still, Even though it's a removable discontinuity, technically this function it still has a discontinuity at 2. So that's where the function is discontinuous, at 0, 2, and 5, with 2 being a removable discontinuity. Alright, let's take a look at another example. Now let's take a look at this example. So let's determine where this function, sine x divided by x squared minus x, has discontinuities, and let's determine if any are removable. So to find where this function has discontinuities, we need to find where the denominator is equal to 0, because we can't divide by 0. Any other place where the denominator does not equal 0, the function will be continuous, as I've noted down here. So just note that the limit as x approaches c of sine x over x squared minus x will equal sine of c over c squared minus c, and this quantity will exist as long as the denominator here does not equal 0, in which case the function will be continuous. So the only place we need to worry about the discontinuities occurring are where the denominator is equal to 0. So let's find those discontinuities and see if any are removable. So we set, and of course this implies that, which implies that x is 0 and 1. So that's where we're going to have our discontinuities. So this is where the function has discontinuities. Now let's see if any of these are removable. Well, if we consider the discontinuity 1 first and look at you'll notice that the numerator here, that's approaching the sine of 1, and you can evaluate this on your calculator. Remember, we're using radian measure here. We always use radian measure, and that's approximately 0.84. However, the denominator, that's approaching 0. So this quantity will be approaching 0.84 divided by something that's getting very, very small. This is either going to be blowing up to positive or negative infinity, depending on which side you approach 1 from. So this limit is going to d and e. So therefore 1 is not a removable discontinuity. This limit fails to exist. Now let's consider the limit as x approaches 0. Well, let's write this function as follows. Well, before we do that, let's notice one thing. If I put 0 in here for x and in for x in the denominator, we get 0 over 0. That indicates that this limit may exist, so we need to do further analysis on it. So what we can do is rewrite this as so we just split the function up like this. Notice how we rewrote the denominator as x times x minus 1 and then just split the function apart like this. This is certainly valid to do. Now you'll notice that as x approaches 0, the first term is our friendly trigonometric limit, and this will approach 1. And this quantity, I have no problem putting 0 in here for x. It is approaching -1, and so this entire limit is -1, which exists. So therefore x equals 0 is actually a removable discontinuity. So let's just take note of that. So for this function, our discontinuities occur at 0 and 1 with a removable discontinuity at x equaling 0. And if you wanted to state the interval over which this function is continuous, you would just state it's continuous for all real numbers except 0 and 1, or you could write it like this. So these are the intervals over which this function is continuous. Notice we just removed the 0 and 1 by using the open parentheses. We removed the 0 and 1 from the real number line. Now let's just take a quick look at what the graph of this function looks like. And here's what the graph of this function looks like. You notice that we have a discontinuity at 1. Technically we have a vertical asymptote at x equaling 1. And you notice also that the function is undefined when x is 0. Notice how we have this little open circle right here, indicating that the function is not defined when x is equal to 0. Because technically if we plug 0 in here for x, we plug 0 in here for the x's, we get 0 over 0, which is an undefined quantity. However, the limit as x approaches negative 0 of f of x does equal negative 1, which exists. And you can see that from the graphic down here. So really, we could redefine this function at 0 and just say, okay, let's let f of x equal for x not equal to 0 and negative 1 if x is equal to 0, and then this function will actually fill in that little open circle there and become continuous. But this function as it stands right here is not continuous at x equaling 0, but it does have a removable discontinuity. Now we're going to formally define continuity over an open interval, and we've already been working with that in some previous examples. So here we have the definition for continuity over an open interval, and we simply say this: a function is said to be continuous over an open interval a,b if it is continuous at every point c in the open interval ab. Alright. So let's take a look at two examples here. First of all, let's determine the intervals over which this function, f of x equals 1 over x minus 1, is continuous. Alright, now for this function, notice first that if I pick any value c, any number c, the limit as x approaches c of 1 over x plus 1 is 1 over c plus 1, right? I can just plug the c in for x, and that equals f of c as long as the denominator c plus 1 does not equal 0. So therefore this function will be continuous everywhere except where the denominator is equal to 0. So all we have to do is find where the denominator is equal to 0. Okay. So that's easy enough. All we need to do is set x plus 1 equal to 0. Of course, that gives us back x equals negative 1. And so our function is going to be continuous everywhere except at negative 1. And we can write that as follows. We can say f of x is continuous on the interval negative infinity to negative 1 union. That means and. Okay, so you'll see that written. You can just write and if you'd like. Negative 1 to positive infinity. Alright, so all we did is we just excluded the negative 1 from our real number line. That's all we've done by writing this. Okay, let's take a look at another example right down here. So let's determine the intervals over which this function is continuous. Alright, so all we have to do is find where the denominator is 0. That's where our function will not be continuous. We'll do that first. So if we set x squared minus 1. We'll set that equal to 0. Now before we do that, note that this factors as x plus 1 times x minus 1. And of course, if we set that equal to 0, we get x equals negative 1 and 1. So our function will be continuous everywhere except at these points. So we have to exclude them from the real number line. So our function will be continuous here, here, and here. So we would say f of x is continuous the interval from negative infinity to negative 1, union negative 1 to 1, and from 1 to infinity. Alright, and there's our answer. Quickly, here's what the graph of this function looks like. Notice that the function is continuous everywhere except at negative 1 and 1. Those are where we have some asymptotic behavior of this function. Notice from negative infinity to negative 1, I can graph that function without picking up my pencil. Right? It satisfies our intuitive definition, our imprecise definition for continuity. It also satisfies our precise definition. Same thing from negative 1 to 1. It's continuous. And from positive 1 to infinity, it is continuous. So it's continuous everywhere except at negative 1 and 1. Okay, so that concludes our discussion and of the definition for continuity.